Okay, so this is unit 1.1, one-dimensional motion. Remember, unit 1 is all of kinematics, and it encompasses both 1D and 2D motion. So a lot of these terms and concepts you see here, you're also going to see when we do unit 1, what I'm calling unit 1.2, which is two-dimensional motion, okay, which is vectors and 2D motion. So if we just talk about this, the first thing is we're going to define what motion is. So motion, right, is the change of an object's position with time, right? So, things have to change. So that's kind of a couple of big things here. So if a position does not change, then there is no motion, right? The object is at rest. Okay, so no change equals no motion, right? So you have to change the position for there to be motion. Now what happens is in physics, and most of you guys have taken AP1 or you've taken some sort of physics class, all the values in physics can be broken down into one or two categories. And we're going to visit these terms a little bit more at length in 1.2. So the first thing is a scalar is a quantity that has size or magnitude only. You're going to use both words, but this is the word that you're probably going to see the most, the word magnitude. That just means size, right? That's the number associated with the value, okay? And then a vector is a quantity that has magnitude and direction. So there's your difference, is the idea that vectors, you have to include the direction. Now, how can we represent direction? You can, easy way is plus minus. You can do the compass directions, north, south, east, west. You can do angles. And at the beginning of 1.2, we're going to work a lot with just simply the arrows, or arrows that are drawn in the general direction and relative in size. Okay. Now, here we go. We're going to start talking more about these terms. So position is the location of a particle with respect to a chosen reference point. Now, typically that reference point is the origin, which is essentially just where we set the 0 point for that motion. Okay, so that's like where x equals 0, or your position equals 0, and your time equals 0. Now, once it begins to move, now it starts to change its position. It is set in motion. The change in position of an object is the object's displacement. Sorry, kind of space there for a second. Okay, represented by delta x. Okay, and then now with this being AP Physics C, you will probably see a little vector symbol over the top. So delta x is equal to x minus x0. So it's kind of like your first official AP Physics C formula. It's not a big one. It is measured in meters, okay, which is given M, remember SI units, and it is, as I mentioned, a vector quantity. So we have to include the direction. Kind of in the what's a simple way to say it? It's essentially just a straight line distance from point A to point B. So if I've got an object, right, and the other word, this kind of the scalar would be distance. So that's one path I can take to get there. That would be a greater distance, right? But my displacement is just going to be this straight line path. So the red arrow, that is the displacement, right? And basically what I can do is, sorry, somehow I skipped all the way up there. What I can do, I think I'm a little too close to the, okay, so this is our delta x. And if I'm just given values, I can just simply subtract those to figure out the length of that arrow. Okay, the time interval, right, measures elapsed time as an object moves from its initial position to a final position. Now, and you can see, and I'll highlight this, for the most part, the initial time will be 0, which means whatever your time is, because just like that delta terminology, it is final minus initial, but in most problems, that T0 will be just simply 0, okay? Which means whatever time you're given, that would be your the time that you're going to use in the problem. Now, how do we measure how fast? Okay, there are really two answers to this. Okay, the first one is an object's speed, and more specifically, its average speed, and we'll distinguish the difference between average and instantaneous here in a minute. It is a scalar quantity, right? So we don't care about the direction. We just care that it went from point A, or we care that it traveled a distance in a time, and it went from point A to point B. The formula is very simple, right? It's x over t, where x represents the total distance traveled, right? And t is just simply the time done in. The second answer is velocity. Okay, and with velocity, we abbreviate it, or the variable is v with that with the arrow over the top, and the arrow over the top just means it's a vector. Now, it is a rate in which an object's displacement changes with respect to time. With this being a calculus-based course, this idea of rate, okay, that idea of rate there is very important because when we start doing the actual calculus, we're going to look for the rate of change. The rate of change is the calculus principle of derivatives. Okay? It is a vector quantity. So here we have to include the direction. And the formula, again, we kind of go back to this idea of rate. And it's simply the rate at which the position changes. So change in position is represented by delta x. And then we have our delta t. Okay. What we'll learn later is kind of the calculus version of this formula, where it's dx dt, which just tells you that the velocity is the derivative of the position function. Okay. Now, because velocity is a vector quantity, it's going to change in two ways. Okay. So the first way is that the magnitude can change, which indicates that there's a change in the speed. So the way you can think of velocity, it's speed and direction. And then the other way is the direction can change, which means it's indicating, well, a change in its direction, right? It goes from positive to negative. It goes from 5 degrees to 35 degrees. At any point in time, if you change that direction, you are changing the velocity. Now, once you change the velocity of an object, you're now accelerating it. Okay, because acceleration is the rate at which an object's velocity changes. So again, you can see that word rate again, right? So again, we're changing a quantity with respect to time, and that is our velocity, our velocity. If we're changing velocity with respect to time, it is an acceleration. So acceleration is a vector quantity. Okay, and so we have that symbol again. But again, we're going to learn here in a little bit that the acceleration is the derivative, right, of velocity. And this showed it up to you before, that ddt notation means derivative. Okay. And what it breaks down to be is it's just simply a slope on a velocity versus time graph, because delta is actually the Greek letter d. So as an object travels in a straight line, so as it travels in a straight line, the position, velocity, and acceleration are going to work together to give you an idea of the object's motion. So more along the lines of these two will work together. And so you can tell, like, if these two, so v and a, so the vectors v and a are in the same direction, the object is going to speed up. Now, note that you got two situations where that can happen, right? So my velocity vector could be pointing in this direction. My acceleration vector could be pointing in this direction. Okay, that means the object is speeding up. Now, note that, if we look at the magnitude, right, it is speeding up. Now, if I go the opposite way, let's say I go to the left, right? This is still technically speeding up. It's just that we're speeding up in the negative direction, okay? Now, over here, right, we're not talking about, is the velocity change. We're looking at the word speed, okay? So technically, yes, in those two scenarios, it is both, they're speeding up. Now, how do we slow an object down? Well, v and a are in opposite directions. Okay, I'll write constant speed here real quick, and actually we'll just do it. So if I have a velocity vector heading this way and an acceleration vector heading that way, they're going to work against each other. So this acceleration is going to chop off part of that velocity vector, causing that vector to be smaller. And in the same sense, if I go this way, if I go to the left, and I have an acceleration to the right, again, it's going to chop off that velocity vector and make it smaller. So this would be my new velocity vector, okay? If I do the same thing here, all right, it would be pointing to the right. Just you can see the size of it is smaller. That is slowing down. And then constant speed, well, that's easy. The acceleration is 0, okay? So if I just have a velocity vector, it doesn't matter which way it's pointing. If I'm not adding acceleration to it, this vector will stay the same size, okay? All right, so now in the next part, we're going to break down into motion in one dimension. Okay, so what happens is a coordinate system, and we're going to talk about this a lot over time. So a coordinate system has two essential features. One is an origin to define 0, right? That's why we set it. Okay, we need to know where the object starts and where it ends. And then here you have an X or Y label with units to indicate the positive end of the axis. So typically you don't define negative, you define positive. So if I have a coordinate system here, positive time, which is always going to be positive, and positive position, okay? And then this is my origin, okay? So that's our coordinate system. In physics, we can do crazy things with our coordinate system. We can just say like this, right? If we're on an incline. Mathematicians don't like that because the positive has to be straight, or the coordinate system has to be straight. We may even do something like this. Okay, and that's just, again, physics makes life easier for ourselves to do these problems, right? So we're not going to try to overcomplicate the problems. If it's easier to flip the axis around, that's what we're going to do. Okay, now a position time graph. So now we're going to talk a little bit about some of these graphs that we're going to see. So position time graph, or what I call a PT graph, is a continuous line or curve showing an object's position as a function of time. So one thing that you can think about is this graph is a number line that is stretched over an axis of time. So if I take a number line, which amounts to my position, right? Because the position is going to be on the y-axis, or the y-axis, right? And I take that number line and now I stretch it over this time axis, right? That's my position versus time graph, okay? Position can go negative, right? Just like a number line can go negative. We're going to work in physics in the first and fourth quadrant because time is often our x-axis, and time can never be negative, okay? So if we just kind of look at this graph here, there's certain things that we can do. We're not going to necessarily right now look at the numerical values, but we're just going to describe what is happening here. So we can talk about how the first thing is that the car starts 10 meters away from the origin. All right. It now drives towards the origin. For roughly 10 minutes, covering a distance of we can put in there. We can also say how it's moved past the origin, and so it covers a distance of 30 meters. Okay, and then rests. So it's going to rest for 5 minutes before continuing on back to the origin for 40 minutes, covering it in 20 meters. Okay, so we could easily plot this, right, in our as a number line. So they started here at 10, and the first leg of the trip, they're going to go from 10 all the way to negative 20. I know my scale is a little weird. They're going to rest, right? I'll put a dot to show rest for 5 minutes, and then they're going to come back to the origin. Okay, which then we can do all kinds of calculations to figure out how fast do they move in that first segment, how was it being accelerated? Okay, and just give you a heads up, anytime you see straight lines on a position versus time graph, it's non-accelerated motion. So that is one thing that's happened here, is that it is completely non-accelerated. Okay, this is an area of rest, so flat lines on position versus time graphs are rest. This would be a negative velocity because the slope of a position versus time graph is its velocity, and then this would be a positive velocity. Okay, if you want to talk about in terms of speed, this would actually be the greater speed, even though it is, if you want to say the smaller the velocity, because of the steepness of this line. So if we look at the magnitude of this line, it's going to be the speed, as opposed to this is a flatter line. Okay, and then so in the next one, we'll just talk about more about this uniform motion before we head on to doing equations and talking about calculus.